All right, good morning. Let me turn this down a little bit. Okay, we're going to get started. So the big question so far has been about end behavior. So I'm going to go over that concept, and then maybe I'll do one of the problems on your practice worksheet. And then if you have any other questions, just post those into chat, and we will give those a shot as well. Okay, so if you have anything else on the worksheet about the introduction that deals with a lot with graphing, and then the second one dealt mostly with word problems. We'll talk about that. Okay, so let me get to here. It is. Okay, we're gonna need to talk about the asymptote. So let me get that out. Okay, and then we will. Let me see if I can find the problem that we were doing. So classwork. We're doing day 12. All right, so I need my snipping tool as well. Okay, so I'm going to just pull up the 2 to the x problem, the first problem on the worksheet, okay, and we'll kind of go through that one together. So here is, let me see if it'll all snip together, okay, something like this. Okay, so this is your first problem that's due, okay, so to talk about end behavior, let's kind of go through everything, and you'll see end behavior as a part of that. So, word problem. Yes, Peyton, we will go over number 5 as well. So, on the word problems. So, as far as end behavior goes, the general idea with end behavior, when we did it before, was we were kind of saying, as x approaches infinity, as x approaches negative infinity, what's happening to the graph? Okay, so we got to actually graph this first before we can see that. So what we did in the video, okay, is just made a table, okay, an XY table. And actually, I think I have this particular XY table, okay, right here, okay. So I have this one already made. Oh, that's part of it. I guess I'll make it real quick, okay. So we just made a quick XY table. You can do anything you want, okay. As far as inputs go, okay, the domain of every exponential function, okay, with rare exception, is going to be all real numbers. Okay, so this is something you can write as this R symbol, right? Or you can write it with the infinities and say pretty much plug in anything you want. Okay, so I'm going to plug in, and just to kind of show a good range of values, I'm going to start at 0, and I'll do a couple of positive numbers like 1, 2, and 3. Okay, and then for the negatives, I'm just going to plug in a couple of negatives because they get very small very fast, so they're not really easy to graph. Okay, so I'm just going to do these 5, 6 values, right? Okay, so if I plug in 2 to the negative 2, if you type that in your calculator, or just think of 2 to the negative 2 as being equal to 1 over 2 squared, well, that looks like 1/4, right? Or if you type 2 to the negative 2 in your calculator, you'll get 0.25, okay? And then I can do 2 to the negative 1, okay? And that's going to be 1 over 2 to the first, right? That says 1/2, right? So that's 0.5, okay? If I plug a 0 in, 2 to the 0, anything to the 0 is 1, okay? And I just want you to notice as I'm doing this, if you notice the pattern is 0.25 doubled is 0.5, 0.5 doubled is 1, right? So as the x values are increasing by 1, my base here is 2, right? So it's kind of makes sense that I'd be doing times 2 times 2 times 2, right? So when I do 2 to the first, I'll get 2. So there's another times 2. 2 squared is 4, so that's another times 2. 2 to the third is 8, so that's another times 2, okay? So this is a quick list of what 2 to the x looks like, okay? And if I graph this, here's what it looks like. We said if I go to negative 2, I'm going to go up to 0.25, which is right here, okay? If I go to negative 1, I'm going to go up a little bit more to 0.5, okay? If I go to 0, I'll go up to 1, okay? If I do 2, I'll go up to 4, okay? 1, 2, 3, 4, okay? And if I do 3, I'm sorry, 1, 2, I'm sorry, 2 goes up to, 1 goes up to 2, that's here. 2 goes up to 4, okay? And 4 goes up to 8, or 3 goes up to 8, there we go. So that's up here, okay? So this point is not accurate. So let's get rid of that one, okay? So this is my sketch, okay? And I'm going to terribly draw this now, okay? Let's talk about the asymptote real quick before we draw it, okay? So I showed you in the video that there's this thing called an asymptote. Okay, and what the asymptote is a line that the graph approaches but never actually reaches. And this is going to be important for end behavior to understand this. So I'm showing you right here a few more input values for 2 to the x, right? So here's the -3, right? We stopped at -2, right? -2 is 0.25. And again, if I'm going this way, if you notice what's happening is divide by 2, divide by 2, divide by 2, divide by 2, right? So if I take 0.25 and divide by 2, right, I get 0.125 if I divide by 2 again, right? So if I keep plugging in 2 to the -3, then -4, -5, I get this set of numbers, okay? So if you notice what's happening is these numbers are getting very, very small, right? Obviously 0.015, 0.007, 0.003, 0.002, right? It's getting very, very small, but it's never actually getting to 0, right? And if you keep dividing by 2, the numbers will get smaller and smaller and smaller, right? We'll keep cutting it in half and cutting it in half and cutting it in half, but we're never actually going to make it equal 0. We're just going to get very, very, very close to 0. And that's what I mean by the graph approaches but never actually reaches, right? This number is getting really, really, really close to 0, but it's never actually getting to 0, okay? So that's what's going to play into our end behavior here, okay? So when I sketch this, I need to put out what the asymptote is, right? The asymptote is going to be, for this type of problem, it's always going to be a horizontal line, right? And for this, I'm actually going to pull out my line tool because I don't think I can write a line that long without it being terrible, okay? So we're going to do a big red line, okay? I don't think there's any arrows. Oh, there is. Okay, let's get rid of the arrows. Big red dotted line, right? And it's going to go right across here, okay? And that dotted line is what this line, right? It's kind of going down really, really fast, right? It's kind of diving, right? And then really, really fast, it turns, okay? And it never quite is going to touch this dotted line. This dotted line is the asymptote. It's going to approach it, get really, really, really close, but it's never actually going to go below it, right? So when I'm sketching this, okay, let me grab my sketching tool. I'm going to sketch this, and I'm going to say it's going to go really, really, really close and stay above this line, right? It's getting slowly closer and closer, but for my graph, counting by ones, you're not going to see a whole lot of that, okay? It's going to ride right along it, okay? And then it's going to start turning and heading up, okay? So this is what an exponential graph looks like. All of your exponential graphs are going to look like this, okay? And to answer your question, Alyssa, you don't always have to put in negative numbers, but you're always going to get this shape. So if you don't plug in negative numbers, you can see that I'm not getting the kind of rest of the turn here, right? Some problems might have a more complicated x up top, right? And for those problems, you might need to plug in more negative numbers to get that shape, or you might not need to plug any at all. So for example, if this was x minus 5, for example, up top instead of just x, you could do without plugging in negative numbers, okay? So you're going to get, it's going to depend on the problem, but the goal is to try to get this type of shape that's flat, 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 and then eventually turns and starts heading up, okay? So to answer your question, there are, it says, are there any times where the points touch the asymptote? The answer to that is no, okay? And I'm actually going to pull up something to show you what I mean, okay? So I'm going to pull up a much more accurate graph, and then we'll talk about the end behavior, okay? Because I think this asymptote point is kind of the key to end behavior, okay? So I'm going to pull up this much more accurate graph, and we're just going to type in y equals 2 to the x again, right? We're going to do the exact same one, okay? Equals 2 to the x, okay? So there's the same graph, right? And you can take a look at this one. It's kind of going down really fast, right? And it looks like right here that it's touching this x-axis, but when I zoom in, right, you can see that there's this tiny little, there's actually a space there, right? And I can go more and more and more negative. Again, right here, it looks like I'm drawing right over the x-axis, but let me keep zooming and zooming and zooming, okay? You can see there's a tiny little gap there, okay? So like your graph's gonna scale enough that it's gonna look like it's touching, right? So if I go all the way over here to like, okay, I'm over at, negative 2 to the negative 12, right? And it looks like, again, I'm touching, but if I keep zooming in, there is actually that tiny, tiny, tiny little bit of space there, okay? So it's going to ride right above this y equals 0 line, but never quite touch it, okay? So asymptotes are numbers that your graph will approach, okay? But they're never actually going to touch that line. It's just going to slowly, slowly, slowly get as close as we can, okay? So this is kind of the summary of the graph, right? And again, your graphs, as you do more of them, they might be reflected, and it might actually be like down here, or it might be like all the way over here, right? It might go up faster, so maybe it'll like only get to here and then start turning up, right? But it's going to be that basic shape and that basic idea. Okay, so let's answer their questions down. Okay, the asymptote for parent functions, and here's what I mean by parent functions. Okay, 2 to the x, 3 to the x, 4 to the x, 5 to the x, those are all parent functions. It's as simple as I can get. Okay, if it just says something to the x, okay, like any number to the x, your asymptote starts off as y equals 0. Okay, this dotted line is y equals 0. Okay, so I'm just describing that my graph is going to kind of dive, get really close to that dotted line, but never quite touch it and never go through it, right? It's just going to kind of slowly keep getting closer, okay? My y-intercept, you can see right here, is at 0, 1. You can just plug in 0 and find out what comes out. So this is just 0, 1, okay? So now we're ready to answer these two questions about range and end behavior because, again, they're related, okay? The range, right, it looks like this number is going up forever. So I'm going to say this one goes all the way to positive infinity, okay? But on the left-hand side, it's not going down forever, right? We said it goes down until it gets to the asymptote, and then it starts flattening out and just riding right above the asymptote and getting as close as it can without ever touching that point. So this dotted line is where the range stops, okay? So y equals 0, okay, is as close as we're going to get to a y value, right? It's going to get as small as we want, but never quite be 0. So this is going to be extremely important. When you write your range, right, I don't want to do the square bracket. That means include 0, right? I don't want to do that. I want to do the rounded bracket, which means get as close to 0 as you want, but don't include 0, right? Any numbers that are close to 0 are going to work, but 0 is not, okay? So that would be my range, okay? And then here's the big one. This is the big question everyone's been asking about is end behavior, okay? This statement right here, as x, I read this as x approaches infinity, right? That is this arrow, okay? This arrow is the positive side of the x graph, right? The x axis positive numbers are right here, right? That number is going up, right? It's approaching infinity, okay? So for this side, we're going to say it approaches infinity, okay? As x approaches negative infinity, which I'm going to use a different color, right? This one, okay, is talking about this arrow, okay? And so this one, on the left-hand side, it's going down and down and down, and we can actually read this as x approaches negative infinity, f of x approaches, well, we can actually see that it's approaching this dotted line, right? So this one's approaching 0, okay? So there's going to be a connection with your range, okay, your end behavior, okay, and your asymptote, okay, because they're all kind of discussing the same thing. This one's saying that the y values will be above or below, depending on the graph, the dotted line. This one's saying that this arrow is getting really, really, really close to the dotted line. And when I talk about asymptote, I'm actually describing the dotted line, okay? So you'll see that range, end behavior, and asymptotes will all have essentially the same number, right? Because they're really describing the same thing. This is the actual y values. This is the arrows, right? Kind of the really, really far to the left y values, right? And this one is where they're actually stopping, okay? So that's kind of the summary of end behavior. Okay, so is there any questions, or do we want to go over another maybe slightly more complicated one from your homework, okay, before you guys turn them in? Do we want to go over like a second problem? Okay? Or did that help for you guys to finish that part of it? Okay, and while that's happening, I'm going to pull up the word problems, which was the thing that's due today, so we can go over number 5. Okay, so exponential growth and decay. Problem number 5. Okay, problem number 5 is actually the kind of the least word problem of them. It's actually asking about the parts, okay? So let's see how we're doing with questions before I move on. Oh, that's graphing calculator. Here it is. Okay. That helped. Good. Okay. And again, if anyone has any other questions, anything on the first worksheet that you want me to go over, let me know, and we'll go over a couple more. Okay, because I'm here till about 1. Okay, but while that's happening, I'm gonna pull out the word problem number 5. So let me zoom in on that. Grab my snipping tool. Okay. So this is about the population of Winnemucca, Nevada. Okay. So let's see about that one. So here is Control C and Control V. Okay, so here's the problem, right? It's the population of Winnemucca, Nevada can be modeled by this equation, where T represents the number of years since 1990. And it's asking what was the population in 1990, and by what percent did the population increase each year? Okay, so I'm going to go back and let me pull up my notes real quick on this, okay, because I want to show you a slide of that one as well. Okay, because this problem is really, instead of asking you about to do a problem and write your own equation, they're giving you the equation and essentially asking you to explain it. Okay, so this is your actually, let me pull this one up first. Okay, so this is your exponential growth information, right? And you can see that for all of your exponential growth problems, it says the amount of increase is usually expressed as a percent. Okay, so if I take a look at this problem or this setup, it's saying that generally speaking, when you write your own equations, you're gonna plug in a starting value, right? Whenever the model starts, okay, you're going to plug in a percentage written as a decimal. So if it was like 10%, you'd put 0.10, okay? And then you're going to be how many increases happen. In our problem, they're talking about number of years. So I'd be talking about how many years has happened, okay? So when I take this, and I'm going to kind of just slide this over real quick and we'll bring it back again, okay? When I take a look at this compared to our problem here, you can see that this equation fits this setup with one small difference. And the difference is that instead of this being written as 1 plus the rate, they combine them together, right? So 1.04, okay, let me grab my pen. Hey, 1.04, I'm going to write this again. This is 6191, and instead of me writing 1.04, I'm going to write that as 1 plus 0.04 to the t, okay? And so if I combine these, I'm actually just going to grab this and pull it right in, okay? With my set, okay. If I combine what we just did, okay, with this thing, okay, you can see how it lines up. Let me see if I can line it up. It's something like that, okay? So the 6191 represents A, which is the starting value, right? And that's their first question, right? Their first question is, what was the population in 1990? And this equation starts in 1990, right? So they're kind of, this question is a disguised way of saying what is the starting value. So the answer to the first question, what is the population in 1990? It's this 6191. That's always your starting value. Okay. By what percent did the population increase each year? Well, my model says 1 plus the rate written as a decimal, and my rate is 0.04. So we're claiming that this went up by 0.04 each year, and that's 4%. Right. So the first question is that the starting population was 6191, and the percent was that it increased by 4% each year. Okay. So this problem is really just checking to see that you can look at the model and kind of summarize what those parts mean, right, if you're given your own model, okay? So hopefully that answers that question, okay? So that's one of the word problems. A lot of the other word problems were you actually writing, like kind of plugging into one of these and then finding a specific value. So that's the one that's due today. That was originally due today. They're actually both due today, okay? And so the other questions that are coming out are about the other worksheets. Let's pull that up, which of course I closed it. So I got to go back and get it again. Okay. That's your radicals test. Okay. And if you have any questions while I'm here, because I just saw it and it reminded me, if you have any questions about the test that you're going to take, if there's anything you want me to explain, I'm happy to go over that too. I might just, after we get done these two problems, I might go over those. Okay. So for this, this graph, there's questions about going over 4 and 5. I'm only going to go over number 4 because they're essentially going to be very similar to each other. So you won't, I don't want to do both. It's going to be the same thing. I want to give you a chance to try some without me. Okay, so I'm going to grab number 4. And then if you still have specific questions about how to connect number 4 and number 4's work with number 5, you can ask those questions, and I'll try to address those, but instead of doing both of them. Okay, so for this problem, the only major difference between this one and this one is that this is 2 to the x, and this one is 2/3 to the x. So it's a fraction base, but everything else is going to be exactly the same, So let me pull up real quick. All right, so another one of the word problems, to find the value. Yes, we'll do one. Just tell me which one you want to go over, Brennan. We'll go over that too. All right, so here's number 4. And the idea with this is we're going to start off, we're going to make a table of values. So we're going to say x and y. Wow, my line drawing ability has gotten worse since we started. Here's x and y. And we're going to plug in numbers. So I'm going to start off. This is where you might be unsure about what numbers to plug in. I'm going to start off by plugging in 0, 1, and 2. I'm not sure which numbers are going to work out. We need to discuss transformations a little bit more, but we're not going to get to that yet. So 0, 1, and 2. If I plug in 2/3 to the 0 power, anything to the 0 power is 1. I'm going to plug in 1. Right? If I raise anything to the first power, it's just going to be that number. So 2/3 to the first equals 2/3. So this one's going to be 2/3. And then if I square this, I'm going to write this one out. This is 2/3 squared. And that's going to be equal to 4 and 9, right? 2 squared and 3 squared, which is 4 over 9. Just to pull out my calculator real quick. Well, actually, I don't need to pull my calculator. This one is going to be equal to approximately 0.44. If I do 4/9. This one is equal to 0.66. So that's my first 3 points. If I graph those, here's what they look like, right? If I plug in or do this 0, 1, and then 1 is going to go up to about 0.66, which is right here, and 2 is going to go to 0.44, which is like right there. So what you can see is that this is really not enough points for me to see this picture, right? This flat end that shoots up, right? I'm starting to see like maybe like this where it's flattening, but I'm not seeing any of the shoot up. So what I'm going to do is I'm going to plug in a couple of negative numbers, and we're going to see what happens. So let's plug in -1. And this is where you might need to go to a calculator. That's fine. So let me pull out my calculator. Calculator. There we go. So I'm going to plug in. Let's see if I can do this. So here's 2 divided by 3, right? 2/3. And I'm going to raise that to, I need a fancier calculator than this to do this. Let's try again. 2/3. And if you didn't know that, you have access to many calculators in Windows, not just the standard one. So there's 2/3. And I'm going to raise that to the -1 power. So I'm going to hit 1 negative. So if I type this in, it's saying 2/3 to the -1 is 1.5. So when I plug in a -1, I get back a 1.5. And that's kind of consistent with how our numbers are going. If you look, these numbers are small, 0.44, and they get bigger, 0.66, and they get bigger, 1, and then they should be getting bigger. So 1.5 is good. If you want to understand why it's 1.5, I'll do one of these. So if I take my 2/3 and I raise it to the -1, that's the same as 2 to the -1 and 3 to the -1. And negative exponents, we just move them in the fraction. So the 2 to the -1 is going to move down, and the 3 to the -1 is going to move up, right? So if you notice, that's 3 over 2. 3 over 2 is 1.5, And then if I do the last one, I'm just going to do it off to the side. You won't see it. 2/3, and I'm going to raise that to the -2 power, And that's 2.25, So when I plug in -2, I get 2.25, So let's graph those ones. So -1 goes up to 1.5, and -2 goes up to 2, and then 0.25, And again, this kind of still doesn't look like the shape I'm going for. So what I'm going to do is I'm going to plug in another negative number, and I guess I'll bring it out, but I'm going to go a little bit more extreme, and I'm going to say, you know what, let me plug in something like maybe over here, right? Because it looks like this is going up really, really, really slowly, and that's because I have a fraction, So I'm going to be a little bit more extreme and say, you know what, let's plug in like -1, 2, 3, let's plug in like -7. Let's see what happens there, So I'm going to go pull my graph out and say 2 divided by 3, that's my base, I'm going to raise that to the -7 power, and hit enter. And that's 17. All right, that's a little bit too big. That goes off my graph. So I'm going to decrease that a little bit and go to the -6. So 2/3, and then I'm going to raise that to the negative sixth. Okay. All right, that's pretty close. We're going to use that one. Okay. So when I plug in negative 6 as my x value, I'm getting about 11.4. Okay. So let me pull that to the side. So I ran out of space going up, so I'm going to put this one down here. Right. And we're going to say when I plugged in a negative 6, okay, I got back about 11.4. Okay. So let's graph that one. 1, 2, 3, 4, 5, 6 is right here. It goes way up here, okay, to about 11 point something. Okay. So you can see that now I'm getting something that resembles that shape where it goes up really, really, really fast, okay, and it's going to hit this point up top. So let's see if I can draw this, okay. Oh, by the way, my asymptote, let's just answer that question now. That is still going to stay y equals 0, okay. And here's why. Let's kind of discuss this real quick, okay. Let me get rid of this, okay. Unless there's something out here, a d value, if you remember transformations, like if there's like a +3, that would take my entire graph and shift it up 1, 2, 3, and that would mean my dotted line would be up here instead. Okay, if there's nothing out here, right, my graph is going to stay at y equals 0. Okay, so just a little something about that. So I'm going to draw my dotted line again. We'll just use this green one. Okay, and there's a dotted line right here. Okay, and the graph's going to approach that dotted line, but it's never going to go below it. And you can see that my points are getting close and close to that. Okay, so if I graph this one, here's what it's going to look like. We'll do it in blue. Okay, so I'm going to say going this way, my graph's going down, down, and down. It's getting flat. It's going to get really close to that line and kind of ride right along there. Okay, so that's my getting close to my asymptote. Okay, and then this way, it's got to hit this point, which I lost, which was negative 1, 2, 3, this one, right about here. Okay, it's going to come up towards this. Okay, and it's going to shoot up real fast and look something like that. Okay, pretend like that's my point. Okay. All right, so that's my graph, and if you notice, it is very similar to this one. This one kind of shot up, going to the right, and this one shoots up, it goes downhill to the right instead of going up. Okay, that is because this one's a fraction, right? If there's a nice whole number, something bigger than 1, this is going to go uphill. That's called a growth. Okay, 2/3 is going to make numbers smaller, right? You can see as my x's get bigger, my values get smaller, right? So this is a decay, right? So that was the difference between an exponential growth, right, where the numbers get bigger and bigger and bigger as I go down the graph, okay? And then this one, we have an exponential decay, okay? So this is my picture, okay? Again, you're just kind of picking any numbers you want, and the reason that you can do that is because the domain is everything from negative infinity to positive infinity. You're just kind of picking numbers that are on the graph, and you're going to keep picking numbers until you get this shape. You know that it's going to start shooting up or shooting down really fast, okay? My range, let's talk about that. It looks like, again, I'm doing like all this whole positive part of the graph is being covered, and it never gets below the asymptote of 0. So it's going to be the same range, okay? I'm going to go from as low as 0, okay? And I'm going to go to as high as positive infinity, okay? But I'm not going to touch 0. So I'm making sure that this left bracket is rounded, not square, right? The square bracket means that it's going to touch 0, right? This one is getting closer and closer and closer to 0, but never actually touching it, okay? So despite not equaling 0, so the asymptote, so let's talk about that. So Patrick's question was, despite not actually equaling 0, the asymptote stays 0, okay? Imagine the asymptote is describing the like wall, right? So we're kind of saying, hey, this thing is going to touch a wall, it's never going to touch the wall, right? So the asymptote is me describing what the graph itself is never going to reach, okay? So you have to separate the asymptote when I'm describing the asymptote as being 0 versus my like range and my end behavior where I'm saying it's going to get close to this wall but never actually touch it. Okay, so when I say that the asymptote equals 0, I'm not describing any of these points, right? I'm actually describing what they will get close to, but never actually get to. Okay, so I hope that helps. Okay, so to answer the rest of these questions, so we can do some of the word problems people are asking about, you can see right here that when I plugged in 0, I got back 1. Okay, so this is still 0, 1. Okay, and then this one's just actually going to be backwards. You can see that on the right-hand side. Let's do the left-hand side. On the left-hand side, that's this arrow. That is on the negative x side, right? The negative x side is the left. Okay, on the negative x side, this one's going up to infinity. Okay, And on the positive side, that's describing this arrow. Okay, on the right-hand side, this is the one that's getting closer and closer and closer to 0, but not quite getting there. So we're going to say x approaches 0. Okay, so because this one kind of flipped over, it reflected in a way to go downhill instead of uphill. It just kind of switched those two end behavior pieces. Okay. So if there's any other questions about graphing, the rest of your problems are going to be very similar to this because they're all, at number 5 was a fraction like this. It'll just be different values that you plug in. Okay, but you'll either get a graph that goes downhill or a graph that goes uphill, but you can see that they're kind of doing the same thing where they're flat in one part and then they shoot up real fast. Okay, this one is kind of flat on the right and shoots up that way. Right, so again, this one's decay, the other one is a growth. Okay, so number 3 on that worksheet. Okay, so let's pause on the graphing. I'll give everyone a chance to absorb a graphing. I had questions about, let's see, can we go over word problem number 7? And wasn't there another word problem one? Got help, prep number 5, for another word. Okay, so Brendan asked about another word problem that finds the values and the number 7. Okay, so let's take a look. So number 7 on my... Oop, that's the wrong one. We don't need the graph anymore, hopefully. So I'm going to leave this. Okay, so we need number 7 on the word problems about growth and decay. Okay, so number 7 says... Did I ask you to do number 7? I'm pretty sure I didn't. I asked you to do just 1 through 6. Okay, so we don't have to do number 7, but I will go over one of the other problems. So we already did 5. 5 is this one. Okay, so let's go over, let's see. So let's go over, I'm going to kind of compare for, let's say 3 and number 1. Okay, so I'll go over number 1 first. Okay, I'm actually going to pull it right out into this same slide. Okay, because number 1 and number 3 are they're actually different from each other, but they're both following the same basic idea. Okay, so for problem number 1, okay, this one's going to be a lot more direct. Okay, so I'm going to just kind of get rid of this problem. I'll leave it. I'm going to get rid of this part of it. Okay, so here's problem number 1. Okay, and it says find the bank account balance if the account starts with $100, okay, and has an annual rate of 4%, and the money is left for 12 years. Okay, so for problem number 1, this is a direct connection to this equation. Okay, and the one thing that you do have to think about, if I go, let's see if I'm in the right one. I'm not. If I go to my other thing right here, right? So we had in the notes for this exponential growth and decay, this one's all about exponential growth, and if you can see it says 1 plus r. We have another one a little later on. This is exponential decay. The only difference is it's 1 minus r. Okay, so one thing that we do have to think about when we're doing these word problems is whether or not the starting value is going to increase or it's going to decrease. Okay, so in this case, because we're talking about interest, okay, that amount of money is going to increase. Okay, so I'm going to say that this is a 1 plus r situation. If I was talking about, for example, like a population decrease, or we sprayed some weeds outside and the number of weeds start dying, and so that's going to go down, right? So you have to look at the context of the word problem and see if the starting number is going to increase or decrease. Okay, this one is increasing. So if I plug in the information for number 1, it's just going to say $100. So that's my starting value. That goes here. Okay, and then I have a rate of 4, so this is 0.04. Okay, and then t is the amount of it. The way I described it was the number of increases. For this bank account, it's described as, let's see if it's described, an annual rate. Okay, so the word annual means every year. So that means that my time is going to change every year. Okay, so I'm going to say that this t value represents the 12 years. Okay, so this is 12. Okay, and then I'm just going to say 1 plus. Okay, so if I go to my calculator, here's how I type this in. Okay, because you want to type it in correctly. I think I'll go back to my simple calculator that's maybe a little smaller. Okay. All right, so here's the way I type this in. I'm going to just type in 1 plus 0.04. I'm going to be lazy and say I can do that in my head. It's 1.04. Okay, I'm going to raise that to the 12th power first. Okay, so if you're having any issues with this part of it. This is going to be an important thing. Okay. Oh, actually, I need my more complicated calculator. Okay. So you have to do PEMDAS. So hopefully you're not doing 100 times 1.04, then getting that answer and raising it to the 12th. Right. The PEMDAS rules say you have to do 1.04 to the 12th first, get that answer, then you're allowed to multiply, right? Exponents happen while parentheses happen, then exponents, then multiply. So we're actually going to do 1.04. Okay? We're going to raise that to the 12th, okay, and get this thing, okay, and then you're going to multiply that by 100, okay? And so I'm getting a final answer of 160.10, right? This is money, so I'm not going to go past 2 decimal places, right? I'm going to say this is final answer 160.10, okay? So this is the balance, right? It looks like we started off with $100 after 12 years. We're up to $160, right? So that's going to be kind of an interest increase of $60 extra because we left our money in the bank account, okay? So that's kind of a very straightforward usage of this exponential growth model, okay? So if you take a look at that compared to number 3, where you're being asked to find that one as well, let me pull number 3, okay? All right. Okay, so for number 3, if I pull that one in now, and we'll put this one below our big important formula, okay, that's down here, okay? We're kind of doing the same thing, but if I go back to let me see if I can pull up my notes one more time. Another important thing that showed up in these notes is this, okay? It says the amount of decrease is usually expressed as a percent, okay? So this value always relies on R being a percent, okay? So whenever we're going to use this formula, they're going to have to say the population increased by 4% or your amount of money decreased by 12% or something like that. If I look at problem number 3, there is no mention of a percent. Okay, if you read it, it says bacteria splits into 2 new cells, thus doubling. Right. So the only way they're describing the change is to just say that it's doubling. Okay. So if it says if we start with 1 bacteria, which can double every hour, how many bacteria will we have at the end of 1 day? Okay. So if I look at this model, here's what I'm going to take from it. There's still a starting value, which in this case they tell us is 1. Okay. But this thing is not going to be 1 plus something because they didn't talk about a percent, right? We're just going to say, oh, what are we multiplying by over and over and over again? But when they say doubling, this is the whole thing, okay, is going to be 2, okay? So we talked about how all of them are something more like this. It's A, B to the X, right? That's the general form, right? This is a specific version of that for percentages, right? Where I can do 1 plus 4%, right? If they don't talk about percentages, I'm going to go back to the much more simple version where I'm going to say, okay, well, what am I multiplying by over and over and over again? Well, if we're doubling, I'm multiplying by 2 times 2 times 2 times 2 times 2 forever, okay? So I'm going to say we're starting off at 1 bacteria. We're multiplying by 2 over and over and over again. How many times are we doing it? It says we're doubling hourly, okay? So this exponent's going to represent the number of hours, and it's talking about by the end of the day, which is 24 hours, okay? So if I type this into my calculator, let me clear out all this other stuff, okay? We're going to say 2 is going to be raised to the 24th, okay, which is gigantic. And then I'm going to multiply by 1, which in this case isn't going to do anything. All right, so it looks like if I take the number 1 and I double it 24 times, it looks like I'm left with 16,777,216. 777,216, okay? All right, and that's my my total number of bacteria happening after 24 hours, right? Started off at 1. After 24 hours, I'm at 16,777,216, okay? So that's the idea with the word problems, okay? So is there any other questions we want to go over? Let's see look at the chat real quick. Number 3 on that worksheet. So Catherine, did you mean number 3 on this worksheet, the one that I just went over, or number 3 on the graphing worksheet? And I think I answered all the other questions that I see. Okay, so let me go back to my... Let me take a look at number 3 on the other one. Okay, so number 3 on the graphing worksheet is very similar to this one, right? So I'm not going to go over that one. Oh, it's very similar to this one, right? It's just a fraction to the x power, right? So that's going to be an exponential decay. It'll look very similar to this, right? In fact, a lot of the information will be almost the same, right? Just with different x values. Okay? So I think I went over a lot of the stuff. Number 3 on the graph worksheet. Okay, so I'll go over one more graphing problem. Let's do it. Okay. All right, so let's go to number 3. And this will be the last graphing one I do because I think we've seen a bunch of them now. Okay, but if you have any general questions, if you're like maybe doing number 5 and you're not sure about what the answer is, I can at least talk to you about what you should have there instead of doing the problem specifically. So let's do number 3. And if you're good with this, if you're okay with number 3, you're welcome to go if you'd like. Don't have to stay here the whole time I'm here. But just really quick, as I'm kind of setting this problem up, just to tell you about the test and how that's going to work. So I posted the tests online. I'm glad it's clear, guys. Okay, so for the test that's going to be due the week, so next week you guys are on spring break. The week after that, we're going to have a full week where we just do 2 assignments like we've been doing. And there'll be live streams and all for that. The test will be due at the end of that second week, okay? So 2 weeks from today. And everyone has essentially I think it's 15 questions, okay? And everybody has the same test written in the same order, but everybody has different problems. So I made 90 versions of the test, okay? So you need to click on the Excel spreadsheet, and next to your student ID number, you'll see that there is a file number. It'll say test number. Okay, that you'll see that the tests are counting by 3s. That's because that's the number of pages that I had to generate for each test. So it'll go from 7 to 10 to 13, whatever. So next to yours, it'll say like in my file list, it'll say like test 312 or something, and that would be your test. Okay, so you'll go on and do that test, and you'll post it to the assignment. And inside of that, there's an ID number that I can match it up to a key. So everyone's essentially going to take the same test, but a different version of it. Same level of difficulty. It's generated by a computer, so it's not any harder from one test to the next. It's just that this way everybody can show me what they know without just being able to look at someone else's paper. You'll have your own to try. Okay. All right. So let's take a look at this last problem. So this one's a little bit more straightforward because it's a half, right? The fraction's a lot nicer. So I'm going to make my XY table. Okay. And I'm going to generate some values. I'm going to generate the standard like -2, -1, 0, 1, 2. Okay. And again, you might have to experiment with these numbers depending on what the base is. Okay. So if I plug in 0, let's do the easy ones. 1/2 to the 0, anything to the 0 is 1. Okay. So that actually answers my asymptote question. What happens when I plug in 0? When I plug in 0, I get back 1. Okay. That's what the y-intercept is. Okay. Anything to the first power. So 1/2 to the first power is just that number back. So that's 1/2. Okay. And then 1/2 being raised to the second power, I'm going to say 1 squared is 1. Okay. 2 squared is 4. Okay. So the 2 is going to be the 1/4. I'm just going to make decimal versions of this. This is 0.25 and this is 0.5. Okay. So if you're a little unsure about the negative exponents, again, here's kind of those written out. If I do 1/2 to the -1, okay, that's going to be equal to, if I kind of give the -1 to both of these, it's going to be 1 to the -1 and 2 to the -1. Okay. If I flip these, it's going to be 2 to the 1 and 1 to the 1. Okay. So that looks like 2 over 1, which is just 2. Okay. And if you notice what happened is that kind of flipped this over. So watch what I do for the second problem. Instead of me like distributing the -1, I'm going to say if I do 1/2 to the -2, again, you can just type this in your calculator too. It'll get you the same answer, but you'll see that you'll eventually get quicker at just doing them without the calculator, and it'll save you some time. I could actually flip this over, right? If I have a negative exponent around the fraction, you too, Brennan, have a good spring break. Enjoy your week off, okay? I'm going to flip this over and say this is 2 over 1, okay? And instead of my -2 being negative, it's going to flip over and be positive. Okay, so that's one way you can handle negative exponents around fractions is flip over the fraction, and then that changes the sign. Okay, we're essentially doing the same thing as we did up here, but instead of like giving the negative to each of these separately and then you flipping them there, I'm just flipping over the whole fraction. Okay, and then this one is going to be 2 squared and 1 squared, which is 4 over 1, which is really just 4. So when I plug in -2, I get back a 4. Okay, and you can see the pattern. The pattern's working. This one is halving, right? So as the values increase, it divides or multiplies by a half, multiplies by a half, multiplies by a half, right? So that's kind of working out. Okay, so I'm going to graph this. Okay, so let's actually, before we graph, let's state this first. The asymptote is going to be y equals 0. Okay, the asymptote will always be y equals 0 unless there's a number sitting right out here that's being added to. Like if my problem was this, let's say it was y equals 2 to the x, and then there's like a -4, right? We call this the d value, right? If there was a d value of -4, that would cause the graph to shift down by 4, and then my dotted line would be down here instead. If there's nothing at the end of this being added or subtracted, your asymptote's at 0. Okay, so I'm going to grab my dotted line. Okay, and I don't know, we'll use this pink one instead. I hope it's not gigantic. Oh, it's gigantic. I can't use that. Okay, let's make it smaller first. We'll do this thickness. Okay, and we'll get rid of these since I'm here. All right, so here's my asymptote. Okay, my domain is always everything. So I'm going to say that this is from -infinity to infinity. Okay. Again, the only time this will not be -infinity to infinity is if my exponent gets really weird. Like if there was like a square root symbol in my exponent, that's when things would get weird. We won't see anything like that here. Okay, so I'm going to say y equals 0 is my asymptote. Here are my points. Let's start graphing them. It looks like, again, 0, 1. Okay, 1, 1/2, which is right here. 2 is actually even smaller, so it's like right there. Okay, and then on the other side, I can see -1 goes up to 2. Okay, and -2 goes up to 1, 2, 3, 4. Okay, so I'm starting to see that increase. I'm just going to add some extra points without showing the work for them. If I plug in a -3, I get back 8. Okay, so we can see the rest of this graph. So 1, 2, 3 goes all the way up to 8, and you can see that it's starting, the points are starting to get further apart. Like from +2 to 0, like I didn't even increase by 1, right? I went from 0.25 to a half to 1, and then from 1 to 4, or from 0 to 3, right, going more that way, I went to up 1 unit, then 2 units, then 4 units. Like, so it's starting to go up really, really fast. So this is my graph. Okay, if you notice, this is almost the same graph. Sorry for my terrible graphing skills. It's really hard to do with these writing slates. This graph is almost identical to this graph. Okay, the only difference is that these points took a little bit longer to increase, right? But they did eventually go up there. So this one and this one are almost the same, with the exception of like how quickly it's shooting up in the air. Okay, so that's my sketch. Okay, my range is the same. It's just going to go as low as 0, right? So my asymptote's at 0. So I'm going to start my range at 0, but not including 0. So I'm going to put a rounded bracket, okay? And it's going to go up forever. So I'm going to say going up to infinity, okay? And I need to look at my arrows. Okay, my arrows in this case, my positive x arrow, that's this first one, it looks like it's approaching 0, right? It's approaching the asymptote, okay? But on the other side, okay, it looks like it's going up forever. So this one, we're going to say that the left-hand arrow, the negative arrow, is approaching infinity. Okay, so that would be my sketch for that. Okay, so is there any questions? That's like the whole problem for that one. And you'll see that again, if you look at the work for 1/2 and for 2/3, it's almost identical. If you notice, the end behavior is the same, the y-intercept's the same, the asymptote's the same, the range and the domain are exactly the same. There's nothing different between these at all. The only time these things are going to, some of this information is going to change is, again, if we start getting more complicated problems with like a plus or minus here. We didn't see any, but if you see a negative sitting out front, right, like -5 times 2/3, right, that might change the range and my end behavior a little bit. Okay, but that's really the gist of it, is that the range, the end behavior, and the asymptote will all be connected to each other. Okay. So if there's no other questions, it's approaching 1 o'clock, okay, and it's the end of your day. It's the end of your fourth quarter so far, because starting on Monday you're on spring break. So you won't get any assignments on Monday. You'll be off for the week, and then the following Monday, you'll get the next new assignments for exponential growth and decay, which I think we continue with for a couple days. We're gonna do, excuse me. Okay, we're gonna do probably one more day of exponential growth and decay. And then I'll give you a kind of a summary practice to wrap up this little bit of topic, and then there'll be another little mini quiz, assuming that this radicals one that we try out, assuming it works out okay and everyone doesn't have any issues. You'll have another small quiz that's maybe just 4 or 5 questions on the graphing and the exponential decay stuff. Okay, so I'm gonna hit pause. I'm gonna be here for another 5 minutes. So if you have any other questions, just post them into chat. Otherwise, have a great spring break. Hopefully, you can get outside and keep away from other people, but get outside and enjoy the weather a little bit because I think it's supposed to be nice on Monday. So, have a good spring break, and I will talk to you guys next. Probably Wednesday after spring break will be the next time I'll be on the live stream. So, enjoy your spring break and enjoy your weekend.